and we'll move along. Our next speaker is Ali from UQ, and he'll be talking about the halo around Mount Isa. Thanks very much, Ali. Would you like to share your screen?
Yes, sure. Thanks, Karen.
I'm just seeing a, oh, there it is. Excellent. Thanks,
Okay.
Ali.
Can you see that's okay?
Yes, yes. Thanks.
All right. Hello, everyone. My name is Ali Parchegani. I am a PhD candidate at Sustainable Minerals Institute, BRC. I'd like to talk about the mineralogical and geochemical halo of the giant Mount Isa system using hyperspectral and XRF core scanning technology. First, let me start with a bit information about the halo study. Hydrothermal alteration around the mineral deposit commonly forms halo that provides a target which is much larger than the deposit itself. And the mineralogy and the geochemistry of the alteration halo provides an indication of the proximity of the mineralization, or in the ideal case, a vector toward the ore deposit, which can be useful for the new discoveries. The key point is that the deposit often have a very small footprint and are easy to miss in drilling. But if you understand the halo, the target becomes much bigger, and this has a potential to improve the discovery rate. So how to understand halo? To define the footprint of the deposit, we need to develop a method that fully integrates the wide range of complex geological, structural, mineralogical, geochemical, and geophysical data using all sorts of techniques. Mount Isa deposit is one of the world's great base metal deposits, which prior to mining contained resources of 255 million ton at 3.3% copper, and more than 150 million ton and at 7% zinc, 6% lead, and 150 gram per ton silver. Mount Isa Basin, located in the northwest Queensland, is a paleo to Mesoproterozoic, and is the host rock and the host unit for all the world-class zinc, lead, and copper deposit at Mount Isa and the George Fisher. Here's the geological map, Mount Isa deposit itself, and the George Fisher deposit further to the north, and the Orchid Shale, the host unit for these deposits. The primary goal of my project is to develop a model that improves the understanding of mineralogical and geochemical characteristics of Mount Isa deposit's footprint. We are using an excellent collection of core in this study. These samples are really important as they represent a lateral sample through the stratigraphic units extending up to certain kilometers away from the Mount Isa mineralization. That gives us opportunity to study the same units from the economic mineralization to the lowest grade. Here is the 3D view of the Orchid Shale, and the geological cross-section map really is marking the position of the copper, lead, zinc ore bodies, and the location of the drill holes through the Orchid Shale up to a certain kilometer away to the north. Fortunately, they've been a new developed methods which are much faster, more accurate, and non-destructive, such as hyperspectral imaging. A good way to identify the minerals or define their properties is to study how light interacts with them. Hyperspectral imaging examines examines how light behaves in the target and recognize the minerals based on different spectral signature. Hyperspectral camera records the target in the 10 to hundreds of wavelengths and will provide great amount of detail compared to RGB image. We are using TerraCore hyperspectral data, and TerraCore hyperspectral data measures the shortwave, infrared, and thermal infrared. Here are some of the example of the hyperspectral data. Well, as I said, hyperspectral imaging generates dominant mineral maps by matching pixel spectrum with the mineral spectral library. As you can see in this first graph in the left, this graph represents calcite and matching calcite spectrum with the using shortwave infrared scanning, and the next one belongs to the colorite, and the last one is matching spectrum with the quartz spectral library using long wave infrared or thermal scanning. Another method that will be used in this study is high resolution XRF line scanning and high resolution imaging. Mineralize is a new generation of drill core scanner for the chemistry, structure, density, and the photography. It has a minimum preparation, direct scanning in the different type of trays, and availability of a scanning core variant size up to PQ. Mineralizer CS against the traditional methods performs a fast, continuous XRF scanning and non-destructively generates high resolution analysis along the full core length and in conjunction with the high resolution photography. Here we can have a look at some of the XRF results. In this slide, we need to utilize the line scan XRF geochemical data to understand the key exploration vector elements such as lead, zinc, copper, manganese, arsenic, and gallium from the known mineralization to the longer distance, and evaluate the potential correlation between the stratigraphic units, stratigraphic house units, and the measured mineralogical and geochemical halos. These XY plots represent the distribution pattern for manganese, zinc, and gallium from the ore bodies up to 11 kilometers to the north. The great correlation between zinc mineralization halo and the manganese distribution is noticeable, and also gallium, and so gallium is following this trend. Another interesting observation would be the manganese distribution pattern through the Orchid Shale members. This plot represents the manganese distribution from Mount Isa deposit up to 9 kilometers away to the north. Sample value being categorized by size and the colors, and here's dark blue shows the less than 0.8% manganese, and the purple is the highest up to highest value in samples and represent up to 3% manganese. As you can see, within the race course, manganese abundance is low to mid-range in value. And this trend decreases from the ore bodies dramatically and finally disappears from about 7 kilometers away from the ore bodies. An interesting observation would be the increase in manganese value and the abundance here far further toward to the George Fisher deposit, about 9 kilometers away from the Mount Isa mineralization, and then we can see the increase in amount of the manganese, and it could be the finishing the border of the Mount Isa halo and the beginning of the new system, which is the George Fisher halo deposits. Within the zebra shale, we can see samples much more less manganese and much less high value manganese. But if we go further down to the arenaceous member, the trend starts to pick up. Here is the highest manganese value within the upper Rio Grande in the lower portion of the Orchid Shale. The manganese footprint from the ore body up to 9 kilometers away to the north can be mapped. As we go further toward the ore bodies and lower portion of the Orchid Shale, we can see the manganese value increasing systematically. Then we can define the mineralogy using the hyperspectral imaging results. High resolution RGB image in this left photos represent the drill core samples from K754 drill holes located next to the Mount Isa ore bodies, part of Rio Grande member. And here in the middle, this is the mineralogy. This is the mineralogy using long wave infrared dominant mineral report, and mineralogy, as you can see, defined by quartz, lots of quartz, carbonates and mica, and in the last photo you can see the short wave infrared dominant mineral map and shows the calcite mineralization basically, and a little bit of colorite and muscovite, and basically great association between the manganese distribution and carbonate mineralization can be observed at the lower part of the Orchid Shale, close to the part of the Rio Grande. The Mount Isa halo is huge and extends more than 10 kilometers to the north within the Orchid Shale. And that gives us the encouragement to understand the halo in much more detail. Excellent collection of core will be used in this study, and they represent a lateral sample from the economic mineralization extending up to 7 kilometers from Mount Isa ore bodies to the north toward George Fisher deposits. New developing scanning methods give us the potential to better understand the elements distribution pattern. Development of an integrated geological model will improve the understanding of mineralogical geochemical characteristics of the footprint of the Mount Isa deposits. Also, understanding the halo may provide evidence regarding to currently controversial deposit genetic models. Thank you.
Excellent, Ali. Thanks very much. It's a great summary and obviously early stages for your PhD, but we've got a lot to look forward to as the results come in. There's a couple of quick questions here for you if you want to stop sharing your screen. Jan has asked, how do you differentiate syn or to post or alteration assemblages and footprint using these methods?
Sorry, could you repeat your question?
How do you or are you trying to differentiate between syn or and post or alteration?
To be honest, we are not. I'm not on that stage yet. At this stage, I'm just trying to have a look at the mineralogy and the geochemistry from the scanning methods. Thanks. But it's gonna be follow up with that.
Okay, thank you. From Ben Andrew, thanks for your presentation, Ali. Do you expect the halos you are seeing to be useful in vectoring to copper mineralization?
Actually, it's a part of this project is looking at the Mount Isa, the deposit halo, which is the copper, lead, zinc, and basically one of the major one is copper. But using the other elements, which is unusual, but such as manganese or gallium or arsenic. Or so.
But vectoring towards copper mineralization as well as lead, zinc, or both?
Both.
Yeah. And from Alex Brown, you're getting a few questions here. I'll do one more, and perhaps we can follow on in the discussion because we should keep going. So Alex says, do you know how the mineralizer was calibrated? The gallium values look like they're in hundreds of ppm, which are exceedingly high.
Well,
I can step in and answer that question if that's of any help. Alex, so there's the Mineralize has had for the last probably 2 or 3 years a system set up at George Fisher, and so they're you know, I think often with these systems when they move into a new environment, there's a settling in period where they you know, they learn what works and what doesn't work. Mineralize has well and truly been through that period for these rocks, so they have a series of standards that are pretty you know, that are pretty well calibrated to deal with this environment.
There's also a related question from Ben in the chat about gallium, and he's asking if the gallium is known to be in sphalerite or could it be in an aluminium phase?
Sorry, Ali, do you know?
Yes.
Oh, sorry. Do you know if the gallium is in the sphalerite?
No, I'm not on that. I'm as you know, I'm in the really early stage of my PhD. So.
Okay.
But what's the correlation between gallium and zinc in the data? Well,
the zinc and gallium is having really showing actually really good relationship as I showed on that slide, and it's one of the actually the elements showing really good correlation between the zinc and lead ore bodies.
Okay, so unfortunately we'll have to move along because we've got 2 more speakers. So Ali, there's 2 more questions there. Perhaps you can have a quick look at and we can chat more afterwards.